Game enemies don't just move at random. They scan, they choose, they react, and sometimes they even outsmart you. The question is how? How do virtual agents decide what to do next and when? Or how a robot decides whether to attack, hide, move, and stop, or just stand there doing nothing like it forgot what it was doing? It is not magic, it is not guesswork, it's logic wrapped in structure powered by something deceptively simple. Behavior trees. They are the brains behind the smartest AI you have seen in games, in simulations, in robots that move through the world like they know something. And once you understand how they work, you will start noticing them everywhere, not just in code, but in nature, in systems, even your own decisions. This isn't just a computer science concept. This is a look inside the mind of AI. AI agents don't just move, they decide. And the smarter those decisions, the more real, responsive, and believable they feel. Take a look at this poor robot on the left. No decision making, no planning, just blind action. The result, it smashes into the first obstacle it sees and panics. Now, look to the right, that's a smart agent. It asks, is there something in my way? If yes, it jumps. If not, it keeps walking. Simple, right? Sure, but that's all it takes to go from frustrating and broken to smooth and intelligent. This kind of logic is what powers NPCs in games, simulations, and even robotics. In case you're not familiar with NPCs, they stand for non-playable characters. They may look like simple background characters, but under the hood, they are making fast, real-time decisions that shape how they interact with the world. Smart AI doesn't guess, it doesn't stumble, it chooses. So now let's talk about finite state machines, the old school way of building AI behavior. They were fine at first. You define some states, wire them together, and call it a day. But as your AI gets more complex, more actions, more transitions, more edge cases, FSMs quickly spiral out of control. Each new behavior creates a new threat in the web. And pretty soon, you're staring at a mess of conditions, triggers, and bugs you didn't even know you invented. One new action, 10 new problems. This tangled logic makes your AI fragile, hard to scale, and even harder to debug. Now compare that to a behavior tree, a clean system that organizes logic in a modular, reusable way. Each branch handles a specific decision. Each node does one job. Instead of chaos, you get clarity. Instead of a sad robot stuck in an existential crisis, you get a smart agent that adapts and reacts without falling apart. So how video game enemies always seem to know exactly when to patrol, when to investigate weird noises, and when to chase you like their paycheck depends on it. It's not voodoo. It's something called the behavior tree. So let's walk through how AI agents make decisions using something that looks like a colorful family tree. So again, what is a behavior tree? Imagine a decision-making flowchart, but for a robot. The AI starts at the top and works its way down, trying to figure out what to do, like a very committed intern. It's a smart to-do list, but instead of making coffee, it's deciding whether to patrol a hallway or remind you why you quick saved 5 minutes ago. Behavior trees are made of different kinds of nodes. At the top is the root node. That's where everything starts. Selector node. The selector node is like, what can I do today? It goes through its children and chooses the first one that doesn't completely fail. If the first behavior doesn't work, it tries the next one. Kind of like when you're hungry, go to Costco, buy 47 snacks, try them all, and somehow you're still hungry. Sequence node. The sequence node is different. It's a checklist. The AI says, I'm going to do all these things in order, or I'm doing nothing. If anything in that sequence fails, boom, the whole thing stops. Parallel node. The parallel node lets the AI multitask. It can monitor the player's position and update its awareness at the same time. It is the digital equivalent of walking and chewing gum. Subtrees and reuse. You'll also see things like subtrees. These are reusable chunks of behavior, like investigate noise. Instead of copying and pasting logic everywhere, we just reuse the same subtree efficiently. Patrol behavior. The patrol branch is where the AI wanders around. It checks patrol points, chooses a random one, and moves there. If nothing weird happens, it just loops. While doing this, the parallel node lets it keep an eye out for the player or update its awareness. Investigate behavior. Then there is the investigate branch. Let's say the AI hears a noise like a poorly thrown bottle. It moves to the location and checks things out. If it finds nothing, it might return to patrolling, but if something is up, it switches to the next branch. Attack behavior. This is where things escalate. If the AI sees the player, it checks visibility, confirms the player is actually there, and attacks. This decision flow from noise to suspicion to violence is powered entirely by the tree. It's like a drama queen with algorithms. Lastly, I would like to talk about a real-time ticking scene. Imagine you're designing the brain of a robot guard in a video game. This robot needs to patrol the area when nothing's happening, investigate suspicious sounds, attack the player if they show up. Now imagine that every single moment the robot asks itself, what should I do right now? That's what real-time ticking is. The robot constantly reevaluates its decision many times per second based on what's going on right now. It doesn't just make a decision once and stick with it. It's rechecking constantly and switching behaviors if needed. That is what real-time ticking is. It's like your AI is thinking, okay, let's recheck everything again. Is the player visible? Yes? Then attack. No? Keep patrolling. Every tick reevaluates the environment and updates the behavior accordingly. Final takeaway. Behavior trees are more than just a clever way to organize AI logic. They are a reminder that structure matters, not just in code, but in how systems learn, react, and evolve. By breaking complexity into branches of possibility, behavior trees help agents make decisions that feel intelligent, responsive, even lifelike. And here's the twist. That logic, that branching, it's not just for machines. Nature does it. Brains do it. Organizations, languages, even families. Trees aren't just a data structure. They are a blueprint, one that shows up everywhere, from the roots of biology to the architecture of AI.